So this is for review quiz chapter 6, and the first one we have is to determine the missing value in this probability distribution so that it actually is a discrete probability distribution. And the main thing to note here is that probabilities need to add up to 1. All the probabilities together have to be 1. So really all we need to do is figure out what is missing so that it adds up that way. So we have 0.18, 0.35, 0.29. Let's go to a calculator. 3.5 and 2.9. We have 0.82 as the total so far. So what we're missing is 0.18. That will give us a probability of 1. So 0.18 is our answer. Check that. And that's correct. Okay. For this next problem, we have a probability distribution already noted here, and it represents the number of hits a baseball player obtained in a game over the course of a season. Okay. So we have verified that this is a discrete probability distribution. In other words, we need to verify that all these things are between 0 and 1, which they are, and that the sum of all these things add up to 1. Well, that's easy to do. Just compute the expression. And all we're going to do here is we're just going to sum up over this entire column, right? Those are all the probabilities. If we just sum up the column, as you can see, we get 1. So yes, this is a discrete probability distribution. All probabilities are between 0 and 1. And the sum of them is equal to 1. Okay, now I want to graph the probability distribution. And we already have it in StatCrunch, so let's go ahead and use this to graph it. So, okay, so to graph this, we can look at this as a custom calculator, because what we have here are individual quantities with certain weights or probabilities to them. So we can do custom calculator. Again, that was stat calculators custom. And then you're going to do the values are x 0 through 5, and the weights or the probabilities are p of x. If we compute this, that'll actually give us a graph of this thing, which we can use for the problem. So the problem says which one is it? And I believe it's B. Let's check it again. Yep. B looks like that. Okay. The distribution has a one mode, right? The mode is the highest value, and the highest value is right there. It has one mode, and you can see that it has a tail going off to the right-hand side. So it's skewed to the tail or skewed right. Okay, now compute the mean. Well, that we already did. Here in StatCrunch, it actually will compute the mean for you like this. So 1.6333. And what are the following interpretations of the mean is correct? Okay. In any number of games, one would expect the mean number of hits per game to be the mean random variable. I think that's correct. You'd expect the mean number to be what you get. The observed number of hits per game will be less than the mean. Nah, it'd probably be around the mean, right? It may be less, but you wouldn't expect that. The observed number of hits per game will be equal to the mean for most games. Not for most games. Over a period of time, it'll average out to the mean, but not for most games. It could be for most games, but that's not necessarily the case. Over the course of many games, one would expect the mean number of hits per game to be the mean number random variable. That sounds actually better, because this one says any number of games. This one says over the course of many games, and that's the key thing, is the law of large numbers. Okay, compute the standard deviation. We already did that again. StatCrunch has a standard deviation right here for us. So we can do that, 1.1831. Make sure, yeah, three decimal places. And what is the probability that in a randomly selected game, the player got 2 hits? Well, this we can calculate here with this one, right? That's asking, what if it's equal to 2 hits? And right there, that's the probability of it being equal to 2 hits. It's also the same thing as just on the data here, 0.2842. That's a probability for 2 hits. 2842. And then what is the probability that in a random selected game, the player got more than 1 hit? Well, more than 1 hit would be 2 or greater, right? So that's going to be 2, 3, 4, 5. So all we have to do is really add up these 4 probabilities. That's the exact same thing as saying greater than or equal to 2. And it'll actually compute that here for us. And that's really just the addition of these 4. What I could do is I could go data compute, and then go ahead and just add these 4 up. I think those are all right. And you can see I get the exact same number, 0.4975, 0.4975. Okay. Check those answers, and they're all correct. Okay, we have a multi-state lottery, the following probability distribution for the cash prizes. So it says the grand prize is 14 million, right? That's what's going to be the cash prize there. And then we have 200,000, 10,000, 100, 743, and then of course most everyone gets $0 because they just lose the lottery. Okay, what is your expected profit from one ticket? And really what we're doing here is we're taking the weighted average. In other words, we're going to multiply the probability by the grand prize and then add that all down, and that will give us the expected grand prize. So I'm going to do that by doing the computation here. I'm going to do this column, the cash prize multiplied by P of X, and then I hit compute there. And you can see this is our weighted weighted calculations here. And so the actual mean is going to be the sum of these weighted, or I should say the expected value is going to be the sum of these weighted averages. So all I have to do is just sum down. I could have done this all in one go. I could have just done sum of the, I'll just build it, of these. But you can take it in steps. You can do whatever you want. And here we go. We get 0.25456. It wants the nearest cent, so 0.25. In other words, the expected prize is going to be 25 cents. So what does that mean? Well, that means on average, you will win 25 cents per lottery ticket. You will not profit 25 cents per lottery ticket. That's because the lottery ticket cost $1. So if you win 25 cents per lottery ticket, but you paid $1, that means on average your expected profit is negative 75 cents. So you're actually losing money per lottery ticket. Okay, now it's the nearest million. How much should the grand prize be so that you can expect a profit? In other words, do we know how much it is to break even? And then to expect a profit, then we know it's going to be greater than that number. So let's go ahead and calculate this. And the way we calculate it is we look for our expected value. We want the expected value, the same idea that we did here, right? We multiplied these two things together and then we added them up, and that was our expected value. What we're trying to do here is figure out how big does this number need to be so our expected value is now equal to 1, because if we expect to win $1 for our lottery ticket and we pay $1, then that is a break-even point. So in other words, what I'm going to do is I'm going to do this process here. I'm going to find the expected value of our random variable here. I'm going to do it by multiplying the probabilities times the first one. So this would be like the grand prize times the probability for that grand prize, so the dollar amount. They're going to add it to the probability for the next highest prize times by the probability, or times by the actual highest prize. That's what I just did to get this number here. I multiplied the cash prize amount by the probability of that, and then I added those up to get our expected value. Let's see what I'm doing here now is I'm changing this amount. So this is going to be our variable x. So really what we have here, this of course just continues on to get to however many you need. Really what we want to do is we want to get an expected value of $1. Then we know that the grand prize, I'll do it as lowercase p, and that's going to be the grand prize amount, and that's going to be multiplied by the probability for the grand prize. The probability for the grand prize is very small, right? It says e to the negative 9. In other words, there's 8 zeros in front of this 5. 1, 2, 3, 4, 5, 6, 7, 8. And that's 5, 4, 6. It's an incredibly low probability. And then we're going to add that to all of the other ones. So the next one, we haven't changed that. All we're changing is this grand prize amount. The next one doesn't change. It's still 200,000 times 2.5 e to the negative 7. We actually calculated that already. That's 0.05. So it's going to be 0.05. That's the expected winning from just that second value. And then for this one is going to be 10,000 times the probability is going to be 0.01732. And so on and so forth. We're going to add up all of them together. So the next one's going to be 0.016. I'm going to do this on StatCrunch just so it's a little bit easier for me to work with. I'm going to do this by doing this. I'm going to exclude this first one because I don't want it involved in our calculation. We don't know how much this needs to be, so I'm going to just exclude it from our calculation. And for the rest of them, I'm going to add 1 there so that they are not removed from the calculation. And the whole point of me doing this is so that I can do compute. And I'm going to do the proportion that we expect to win from each one times this column. So that way, I've removed this first row from our calculations, but the rest of them are the exact same. It's still 0.05, 0.01732, 0.016016, and so on. And that's really what I was doing here. Is I was adding up all of these amounts. This one has a variable in it, so I don't want to add it in, but I want to add up all the rest of them. And I can do that on StatCrunch very easily by just doing the sum. So we're going to go compute expression. We're going to take what we just calculated, and we're going to do the sum. So this is the probabilities, or the expected values, I should say. They're kind of like the expected amounts from these, let's see, what is it? These 7 values for everything less than the grand prize. So really what this is boiling down to is we're adding up all these things to give us that $1 equals P times 1, 2, 3, 4, 5, 6, 7, 8, 5, 4, 6, plus 0.178128576. And now all we have to do is solve this linear equation. So I can subtract this number over. I'll just subtract it over here, and then divide by this number, 0.000. So divide by whatever that is there. So let's go ahead and do that. Once again, I can do this on StatCrunch if I wanted to. All I have to do is go edit, or let's go data, compute, expression. We're going to do one minus this thing that we just found, 0.17812858. That's going to be divided by this probability, which I can write it as 5.46 e to the negative 9. That's the same way as doing this 0.000000445 or 546. Okay, compute that. And here we have P equaling 1.505259 e to the 8th. I'm going to do 1.5052. E to the 8th. That's the same thing as saying 1, 2, 3, 4, 5, 6, 7, 8, or $150,520,000. And the problem itself says to the nearest million. In other words, we need to have 151 million before we can even expect a profit. So really what you can do here is we can change. We already know that this is the cash price, right? We would try to find a number so that this thing would be at least $1. And we increase this to, let's see, it was 151. If I change this and then recalculate, what I've done here is I've just deleted those columns that we don't need. I've changed this cash price, and so now if I recalculate what I did before, the expected value, which is the exact same thing as the sum of the cash price times the probabilities. If we add them all up, now you can see our expected winnings is a little bit more than 1. So we expect a profit in this case. Not a very big profit, but it's still a profit. Okay, does the size of the grand prize affect your chance of winning? So the size of grand prize affected our expected value of profit, but the size does not affect our chance of winning. Those are determined by these probabilities here, and nothing we did by changing this grand prize changed these probabilities. So no, the chance of winning is determined by the properties of the lottery and not the payouts. Let's check our answer. And that's all correct. Okay, how many credit cards do you currently have? And here is the data. We actually have here 100 values, and it wants us to find the mean and standard deviation of this stuff. Now you could of course do it by hand, but this is so many numbers, there's no reason to do that. Let's use StatCrunch to do that. And so for this, we can go stat, calculator, or I should say summary stats, and columns. And what this allows us to do is take data in a column, find whatever we want. We can find the how many there are. It's going to be 100 for n. It's going to find us the mean, the standard deviation, variance, median, mean, all that kind of stuff. If we compute that, here we go. It calculates all that stuff immediately. The mean is 3.1. And the standard deviation is right here. Standard deviation 1.8395. And it wants the 3 places, so it's going to be 1.840. Okay, now it wants us to get a probability distribution. And what we're doing here is we're taking the counts of 1 and dividing it out of 100. So the real question is how many times does 1 show up here? That's how many proportionally it would be out of 100, and therefore you can get a probability from that. We can do that immediately on StatCrunch by doing a frequency table and just doing compute here. What this does is it tells us that 1 shows up 13 times in this list of 100. 2 shows up 31, 3 shows up 28, 4, 13, and so on and so forth. The relative frequency is the same thing as the probability that this happens with this data set. So 13 divided by 100, right? The count is 100. There's 100 total, data points here. 13 divided by 100 is 0.13. 31 divided by 100 is 0.31, and so on and so forth. I'm going to store this data in a table for later use, possibly. Okay, so this is going to be important because it wants this stuff in this table here. So we have, it wants the probability. That's the same thing as relative frequency. So we get 1, 3, 3, 1, 2, 8, 1, 3. Then we have 0.07, 0.01, 2, 2, 2, 1. And that, I believe, is correct. 3, 1, 2, 8, 1, 3, 0.07, 1, 2, 2, 2, 1. Yep. Okay. Now it wants us to graph this distribution and to see what we get. So let's do that next. Here's a simple graph of it. So we have 1 through 10, and each one has a weight attached to it, a probability. So let's go ahead and find the correct graph there. I believe it looks like C. Yeah, goes down, up, and down, and it tails off to the right. So the distribution has one mode, has one highest point, and is the tail's off to the right, so it's skewed to the right. It's always skewed towards the tail. Now, in doing this calculation, you can see that we have the mean. Once again, the mean is the same mean we found last time, 3.1. And the standard deviation here is 1.8303. But it only wants 3 places. And you can see that the standard deviation is actually slightly different. The mean is the same, but the standard deviation changes only a little bit. Okay, determine the probability of randomly selecting an individual whose number of credit cards is more than 2 standard deviations from the mean. So more than 2 standard deviations. Let's look at a calculator here. So our mean is 3.1. And if we subtract 2 standard deviations, that was 1.83. We're going to get a negative number. So we know that we can't have anything that's less than 2 standard deviations. So really we are looking at only more than 2 standard deviations is going to be the plus. So anything that's higher than 6.76. In other words, 7, 8, 9, and 10. If we add up those probabilities, 7 through 10, you can see we get 2, 2, 2, that's 6, plus 1 is 0.07. This result is not unusual because the probability is greater than 0.05. That 0.05 is going to come into play a little bit later on too. It's kind of this normal breaking point between unusual behavior. That can change though. You can have 0.01 be the breaking point, 0.001, so on and so forth. Now, determine the probability of randomly selecting 2 individuals who are issued exactly 2 credit cards. Are these events independent? And the answer is no. Because when we check if the first person has 2 credit cards, right? We're looking at someone, we're saying, do you have 2 credit cards? No. Then we look at somebody else. So this is testing without replacement. So you know the probability is not going to stay the same. It's this way for the first one, right? But the second one changes. However, this isn't hard to calculate because the first person having a credit card of 2, well, we know that's going to be 31 out of 100. That's how you found this probability. It's 31 out of 100, 0.31. 31 out of 100 is for the first person, but now the second person is going to be 30 out of 99 because we're sampling without replacement. So this is the probability of exactly 2 people having exactly selecting 2 individuals who are issued exactly 2 credit cards. Okay, and that's going to be 0.09393. So 0.094, rounding to 3 places. Okay, interpret this result. If an individual is chosen at random, the probability they have exactly 2 credit cards is... No, it's not for 1 individual, it's for 2. Whenever multiple people were surveyed, no, it's not for multiple people, it's only for 2 people. If 2 individuals were randomly selected, surveyed 100 different times, the surveyors would expect about, I think it's this one, they would expect about, times this by 100, we're going to get 9.4. Well, you can't have 0.4 of a person. Or you can't have 0.4 of a survey. So you're going to have 9 surveys that would result in 2 people with exactly 2 credit cards. Whenever a couple applies, no, there's nothing about a couple in here. In fact, if a couple applied, you'd think that would affect the probabilities of the events even greater. So, all right, let's check those answers. And those are all correct. Next one says a binomial probability experiment is conducted, and we have these parameters. So in other words, there's a 0.05% chance of a success. We're trying it, 40 times, 40 trials, and we're asking, what if we got two successes? What's the probability of getting just 2 successes out of 40 trials? Well, you could do this by hand using the formula, or let's just use StatCrunch. Now, we're looking for a binomial probability experiment. So that's going to be a stat calculator binomial. And this allows us to actually choose, if we choose a standard, it'd be how many n? N is 40 here. The probability is 0.05. And we're asking, what is it when x equals 2? Compute that. And there we go. We have our probability right there, 0.2776. 0.2777. That's rounded 4 places. Check that. That's correct. The next one says, what's the probability if n is 7, p is 0.3, and x is now less than 4? Well, we can just change that, right? N is 7, p is 0.3, and x is less than 4. Compute that, and we get a probability of 0.8739, so 0.8740. All right. According to an airline, flights are on time 80% of the time. So that's our success rate here. Suppose 10 flights are randomly selected. Explain what this is a binomial experiment. First off, the trials are independent. Now, one plane being on time might affect the next plane, or one plane being off time might affect the next plane being off time, but I think in general, you would not assume that. You should assume that the flights, if they're coming from different locations, there's no reason to assume that they depend upon each other. We have 2 mutually exclusive outcomes, right? You either are on time or you're not. So there's two outcomes. We've also performed this 10 times. It's a fixed number of times. A binomial experiment can never be unlimited times. It has to be a fixed number. Each trial depends on the previous trial. That means they are not independent, and we do want independence. No, there are only two mutually exclusive outcomes. So this is incorrect. The experiment is performed until a desired number of successes is reached. That's not true. We're just seeing how many times they work or not. And the probability of success is the same for each trial of the experiment. That is true. It's always 80% for the success rate. Okay, the probability that exactly 6 flights are on time, well, that's just a binomial thing again. So we have 10 trials. All right, we have our success rate of 0.8. That's a 80% of success rate. And we're saying the flights are on time or succeed exactly 6. So what's the probability? And it is 0.088. 0, 4 places, so 0.081. Okay, in 100 trials of this experiment, it is expected that 9 are result in 6 flights being on time, because you can't have if you multiply that by 100, you get 8.81. Well, you can't have 0.81 of a time, so it's going to be 9. The probability that fewer than 6 flights are on time. So fewer than 6 is going to be less than 6. You see here we get 0.0327, so 0.0328. Multiply that by 100 and we get 3. Again, rounding to that whole number. Probability that at least 6 flights are on time, at least, is going to be greater than or equal to 6. And you see we get 0.9672. Multiply that by 100 and you get 97 rounded. And finally, probability that's between 4 and 6 flights. Well, between, it's going to be, we're going to use this between button. Actually, between 4 and 6 flights. Again, N and P are still the same. Now we get 0.1200. Multiply that by 100 and we get 12. All right, let's check the answer. And there we go. Okay, question 9, last question. 13 jurors are randomly selected from a population of 3 million. Of the 3 million, 46% are of a minority race. Of the 13 jurors, 2 are minorities. So what proportion of the jury described is from the minority race? Well, the proportion is going to be 2 out of 13, rounded to decimal places. So let's go ahead and do that. We get 0.15. So that's the proportion that we actually have. The probability that 2 or fewer out of 13 jurors are minorities, assuming the proportion of population of minorities is 46. So this is going to be a binomial experiment. And we're saying we have 13 trials, right? 13 selections out of this probability. And we're going to consider our success to be a minority. In other words, 0.46 is the success rate. So we get, there's 13 trials. The success rate is 0.46. And we're asking the probability that 2 or fewer, in other words, X must be less than or equal to 2. And the probability that that's going to happen is 0.0227. So 4, so it's going to be 0.0228. And that should tell you that this is extremely low, right? That's less than 5%. So that's an extremely low probability. So the number of minorities on the jury is not impossible. It's definitely not impossible. It is unusually low, though. You can see that, right? We would expect to be about the percentage. We would expect to be this proportion to be close to this 46%, but it's not. This is a lot lower than it should be, given the population, the composition of the population. And that's correct.